So, welcome back to the third video. Enough theory. As promised, we will now create our first quantum circuit. Let's start with a fun fact. Quantum computers will not need a random number generator anymore. The measurement of a qubit in balanced superposition will be based on real, not emulated, randomness. At least if we use a real quantum computer and not just a simulator. We will use that simple mechanism for our Hello Quantum World program, an 8-sided die. The idea is very straightforward: to put 3 qubits independently in a balanced superposition, measure them, and store the results in classical bits. We interpret the bits as a binary representation of a number between 0 and 7. Adding 1 to the result will end up in our 8-sided dice. This program is a combination of a quantum circuit and supporting classical code, here Python, to encode and execute the quantum circuit and to post-process the result from the quantum circuit. Let's start with the quantum circuit for our 8-sided die. It looks like this. You see 3 qubits on the left side, each one in the initial state 0. Then we apply a Hadamard gate to each qubit, which will bring them into a balanced superposition. That means if we measure the qubit, we get 0 or 1 at the same probability. Subsequently, we measure each qubit and store the result in classical bits. See them at the bottom. Maybe you pause the video here to look this through. Now, as the next step, we need to encode this circuit in a Jupyter notebook using Python and the IBM Qiskit package. And this is how it looks in a Jupyter notebook. This is the Python code using Qiskit to encode and execute the quantum circuit as defined, and afterwards post-process the quantum results. We will use Qiskit's simulator for a quantum computer, but a real quantum computer could be used as well. Before we can use Qiskit and its simulator, the 2 packages, Qiskit and Qiskit Air, need to be installed using the pip command. Initially, we import from Qiskit the quantum circuit class to create and encode a new quantum circuit and the standalone function transpile to prepare the encoded circuit for execution, as well as Air, the simulator module of Qiskit Air. We initialize a new empty quantum circuit QC with 3 qubits and 3 classical bits. The 3 qubits will all be initialized in the state 0. Now we need to build the quantum circuit by adding gates and measurements sequentially. Similar to encoding a neural network using Keras. As a first step, we add a so-called Hadamard gate to each qubit, one after the other. After this, all qubits will be in an equal superposition. Then we add a measurement to each qubit, writing the measurement result into a classical bit of the circuit QC. Again, one after the other. First we measure qubit 0 and write the result into classical bit 0, then the same for qubit 1 and qubit 2. Now our circuit is complete. We can check the design of the encoded quantum circuit by using the draw method as shown. Yes, looks as intended. Now we need to define the backend on which the circuit shall run. This can be specific quantum hardware or a simulator. In our case, we use the Air simulator of Qiskit. Then we need to prepare the circuit for execution on the chosen backend. In our case, on the simulator. This is called transpilation. We transpile our QC circuit. It is like optimizing and compiling it. We can also print the transpiled circuit. Looks still the same. And finally, we execute the encoded circuit on the back end. As quickly discussed in the measurement section earlier, it is often important to get many measurement results to understand the superpositions of the qubits, as it is a statistical process. But for our 8-sided die, we need just one run. That means one shot is sufficient. The result we get back, the 3 readouts of the qubits, is then translated into a 3-bit binary digit. We add 1 and get the result of rolling our 8-sided quantum die. This was our first quantum computing program. Congratulations. On the qubit-lab.ch webpage, you will find the Jupyter Notebook version of the shown code. You can directly access it through Google Colab. Just hit a button. All very convenient. Test it out. The address is www.qubit-lab.ch. CH stands for Switzerland, as this is a Swiss page. I encourage you to have a look at the code and verify our results. Maybe modify it a bit, for instance towards a 16-sided die or whatever you come up with. On the Qubit Lab webpage, you will also find the updated Qiskit 2.0 code and the Google Circ code for the same circuit. So you can compare the most popular environments on quantum computing. The logic is the same, the implementation differs slightly, as you might see. In the next episodes, we look at the possible gates of quantum computers and how they work on qubits, as we used here the Hadamard gate. We will also look at how a phase shift can be used to modify qubit states. Eventually, this will lead to the concept of phase kickbacks as used in current quantum algorithms for real-life applications. But before that, we will quickly do a refresher on complex numbers, vector spaces, and 2x2 matrices, all as simple as possible. If you found this interesting and would like to see more episodes exploring quantum computing, I would greatly appreciate your feedback here or on the qubit-lab.ch webpage. I'm eager to understand if this topic resonates with you and a wider audience. Also, if you're curious about practical quantum computing use cases, or would like to discuss potential applications in finance and beyond, feel free to connect with me on LinkedIn or leave a comment. Thank you for your time. I hope this session sparked your curiosity and motivates you to explore this fascinating technology further, and trust me, there's much more to come. Have a great day.